Thank you very much, Sanjay. So welcome, everyone. It's nice to virtually be here today. And so I was asked to give a fairly broad introduction just to gravitational waves and data analysis. So I'm going to focus this fairly conceptually. I am going to talk very little about the actual detectors, mostly so this is a very theoretical introduction to gravitational waves and data analysis. But hopefully we'll give you an idea of some of the concepts behind gravitational wave predictions and interpretations that lead to the astrophysical conclusions that we've been able to draw from this new astronomy. So let me start out just setting the stage with some of the fundamental concepts that give us our picture of gravitational wave emission. And so this is coming in from our relativistic picture of gravity today, where you start out with the principle of equivalence that, if I am in a free falling elevator with some equipment, everything falls together and I have no measurement of the gravitational effects that may be, pulling me towards some distant planet, unless, you feel the floor, you don't feel gravity. So what we want to do to use gravity as an astrophysical tool is to think more about gravity from distant objects. And so the fundamental idea that's going to generate both our gravitational waves and sort of all the influence of distant objects comes into the gradient of gravity, the change in the gravitational acceleration over a separation. So this is going to scale not as the gravitational acceleration itself, but which is 1 over r squared, but as 1 over r cubed. So the gravitational acceleration of these two balls from a point mass that's far away is slightly different if their size separation is large enough compared to the scale of the change in gravity. And so that lets us notice things like tides. So the Earth, from the gravitational force of the moon, has this relative acceleration, which gives us an equilibrium for the tidal potential of the ocean, which sort of stretches and squeezes in this quadrupole pattern. So if we want to measure gravitational effects, we need some sort of differential acceleration coming from a gradient in gravity. Okay, so our next step then to launch us into astronomy is that we also want to find a radiative gravitational effect. And this naturally is going to fall out from a relativistic theory of gravity, because the changing gravitational pull you feel from a system that has a time varying mass of the right type will not be known to you instantaneously based on the source's change. So any change in the gravitational effects you feel from this distant source must propagate to you in a relativistically sensible way. So this is how we kind of fundamentally expect or end up with gravitational waves. So curvature of space-time changes around moving objects. That change propagates out at the speed of light. So just like any relativistic field theory, we get wave behaviors. And in particular, if you linearize the equations of gravity, you get a wave equation. So just like your Maxwell's equations give you a wave equation that gives you the two polarizations of light. The equations of general relativity linearized give you a wave equation that gives you two polarizations of gravitational radiation, which the effect of which is to stretch and squeeze the distance between freely falling objects. So these nearby objects are feeling a relative acceleration that changes the distances, but similar to, say, the change of the surface of the ocean distance from the tides of the distant moon. And this is a physical effect, which was not really sort of established until the middle of the 1900s, that the distance between freely falling objects had a physical impact, that these waves could carry energy, and that's sort of what gives us their astrophysical influence today. Okay, so what do you need to generate a gravitational wave? Fundamentally, you need a time-varying quadrupole moment. So, you have a monopole, which is just the mass. You have a dipole. That's a little tricky in a system of gravity where you only have one sign of charge. But now you can get a quadrupole moment, sort of with the distance squared coming into the scale of the quadrupole moment in mass. And if it's oscillating, this gravity gradient turns out to be proportional to 4 time derivatives of the quadrupole moment over r. So this is a radiative effect, similar to the 1/r effects you would see in electromagnetism. You pull 4 time derivatives of the frequency, or of an oscillation at this frequency, and you get the mass, quadrupole effect, and a 1/r fall off. So I need a bunch of mass, I need it to be oscillating, and then sort of the standard example, and the one that we've observed, would be a binary orbit, which has some characteristic mass that's moving around a distance, a size of the dynamics of the system, with some orbital frequency. And that particular example lets us relate F and S together, which is going to give us some more concrete ideas about the scale of the gravity gradient effect. Okay, so what does this mean when it hits our gravitational wave observatory? So we're going to have some relative displacement, some change in the length, perhaps measured by mirrors here, moving back and forth relative to some central point. So the idea, if we have here our detector kind of placed in the middle of that stretching and squeezing ring of particles, we get a differential acceleration, which is coming from a differential displacement between 2 points. And that relative displacement, then we had our 4 time derivatives, but we're going to integrate our acceleration twice to get a displacement. So we end up with 2 powers of the frequency. And for a system moving at a characteristic frequency across a characteristic distance, we have a characteristic velocity. And the one that's going to generate a gravitational wave is velocities of matter in the perpendicular to the direction of propagation. So if I look out at my source, I want to see motion of the mass to feel a gravitational wave being emitted from this system. Okay, so we've got mass, it's got to be moving. We've got radiative fall off here, and then just some factors of G and C hanging around to get the units to work out properly. So here's sort of an example of a binary orbit, perhaps seen from overhead or perhaps seen from the side, and the response of an interferometer or some test particles from your perspective looking at the system. So the strain here, when I put in the, so basically a Keplerian orbit to go for the frequencies, the size, and the masses involved, I get something that's proportional to a small number at astrophysical distances. So the distances is where we expect to find some meaningful number of these binaries, where the strain will increase with the mass relative to the characteristic mass of, say, our favorite neutron stars in our local galaxy. And it will also require the orbital separation to be comparable to the Schwarzschild mass or Schwarzschild radius of the mass involved. So the radius at which point mass is so concentrated that an event horizon forms that it turns into a black hole. So this means We need something very compact, moving around by Keplerian orbital rules. Very compact motion is a very high frequency, or is a high velocity orbit. Okay. Now, so this seems like a pretty tiny effect here, but the effect on stretching and squeezing space-time actually reflects a tremendous amount of energy being emitted from this system. So you can, this is totally out of order. Okay, so you can consider the gravitational wave energy flux. It's proportional to the strain squared. You integrate it over a sphere. So this strain expression before integrating, you have to multiply it by the frequency to get the energy flux. This is just the right units for luminosity. You put this all together and you get something that again has an amount of energy that is actually now quite large. There's a c to the fifth here divided by a tiny g. For a compact system, so mass comparable to the Schwarzschild radius again, or sorry, separation comparable to the Schwarzschild radius again, and something that is very sensitive to the velocity involved. So for our binary orbits example, this gravitational wave luminosity turns out to again require the orbits to be small compared to the Schwarzschild radius of the mass involved, and at very high velocity. But then if you can get something orbiting around its companion close compared to the size of a black hole, which is a non-trivial prospect to be sure, but then you can get a huge amount of energy being emitted by this system. So on the order of say 10 to the 60 ergs per second, if you like astronomy units. Okay, so this is what gives us the gravitational wave chirp. We have two bodies orbiting. They're losing energy. The gravitational wave energy carried away is a loss to the energy of the system. They have an orbital energy that's you can sort of estimate from a Newtonian orbit, the kinetic energy, the gravitational potential energy, the Keplerian relationship between orbital speed and orbital distance, and you get an expression for the orbital energy that I can use to convert into an equation that changes my dE dt here into a dA dt with the orbital separation A, along with how the energy of the orbit changes with orbital separation. So this lets me solve for the orbital separation as a function of time. That orbital separation is linked, at least on the sort of one orbit average scale, which we can start with here, to the amount of gravitational wave energy radiated and the amplitude of the gravitational wave strain being emitted from the system over time. And so this is what gives us the characteristic chirp pattern of the amplitude of the wave increasing over time and the frequency of the wave also increasing over time. So here, this is just the strain traveling through space as would be recorded at a fixed distant by a fixed distant observer. Okay, so here's an example. So now that we have the strain connected to orbital properties, when we observe a system and record the strain as a function of time, the frequency of the gravitational wave strain is tracking the orbital frequency of the system involved. So these here, this is a case of two merging black holes. We get a chirp waveform that reflects the dynamics of the orbits of the two bodies as they in-spiral together. And this waveform model also includes merger and ring down, which can be determined in various ways in general relativity, including things like numerical simulations. So we can explore the merger not only with this sort of energy balance starting point, but through a full assessment of the equations of general relativity and how that explains the dynamics of orbiting systems and stirs up resulting gravitational waves that can be recorded by our detectors. Okay, so basics so far then. We need some sort of quadrupole motion, some velocity perpendicular to what you're looking for. You're looking for mass that is moving really rapidly, that's very compact. So objects like black holes and neutron stars that have this coherent motion in a binary orbit are our primary strong sources of gravitational radiation. I wanted to also say a little bit about how the signature of matter comes in. So I've only talked so far about features that are characterized by the mass of the system. But we also see some additional things in the signal. We see spin, which I won't talk too much about, but I wanted to say a little bit about the way that matter is imprinted on the signal we observe. And so if we look now at a simulation not of two merging black holes with horizons, but two merging neutron stars here with surfaces, we can see the radiation emitted in the simulation. And we can also see the in spiral, the post-merger as the stars form this remnant object. And again, in the post-merger now, the oscillation of this remnant object is what's generating the gravitational wave strain, tracking the frequency of oscillation until it collapses to a black hole that settles down. So most of what we see in the detectors today is the in spiral. And if we're going to go beyond just the point mass characterization, that's sort of, or the black hole characterization, to learn something about the properties of the components, we need to look at what other influences from the properties of these two components come into the in spiral. And so for matter, what we're going to see here, which you can see a little bit in this middle panel, is the distortion of these two objects from the tidal fields of their companions. So the tidal field adds to the energy loss in gravitational waves. So when we started before, we had something like, sorry, I'm flipping around my notation a little bit here, but we had our change now in the radius of the orbit as a function of time coming from the gravitational wave luminosity. We'll also have some energy going into deforming the star. And our orbital energy, binding energy, is joined by the energy to distort the star from its equilibrium spherical configuration. So this will modify the equations that describe how the stars evolve, the orbital separation changing over time. And that, and in turn, modifies how the orbital pattern changes over time as recorded in the gravitational wave strain. So this is a fairly subtle effect, but it accumulates over many, many orbits, which is what we attempt to discern when we come to the parameter estimation a little bit here. One note is that, as you might see here, the energy scale required to compete with the gravitational wave luminosity is large. So if you try, gravitational wave luminosity is 10 to the 60 ergs per second near the final stages of merger. If you try and back up a little bit and still pump, say, 10 to the 46 ergs into the system at, say, around 100 hertz from some neutron star resonance, that still may have only a tiny effect on the phase and thus the strain pattern that would be predicted from the signal. And of course, things get a little complicated after this, as the stars collide. Okay. I wanted to note that when we will be talking about the tidal parameter that characterizes the system, but the parameter that we use is defined by linear perturbation of an equilibrium star. It's not something that is directly measured from, say, a numerical simulation like the one I started with. It's the ratio for an isolated star, not quite isolated, a single star, of the quadrupole distortion of the potential around that star due to an external tidal field. So this ends up depending on the radius to a very large power. So radius is the most impact on how the tides are generated in a binary system. It also has this contribution from what's called the relativistic Love number, which characterizes the mass distribution within the star. Okay, we're looking for bulk matter changes to influence the gravitational waves and the gravitational dynamics of the system. For a black hole, this parameter goes to 0. So this, the presence of this quantity imprinted on the orbit is what will indicate that we have a different class of astrophysical object. So when we are describing our waveform models for the gravitational waves coming from an orbiting binary, we'll have the component masses and spin, and we also use this tidal parameter as an effective matter parameter, which has been mapped from this linear approximation through a full analysis, which I won't really get into, but effectively, at least at the level of accuracy which we currently require to model our waveforms, and I think Katerina will talk more about this in a future session, this is what we use to characterize our system. So we have mass, we have spins, and we have this tidal parameter. So how do we take this model of how gravitational waves behave and how they are generated and how they reflect the properties of the orbiting bodies that are stirring them up, and turn this into something we can compare to the data recorded by a gravitational wave detector. So the start point for many of the detections that we've discussed or that we've found so far is a search that requires a template model generated with the kinds of processes I've been discussing so far that we can cross-correlate with the data, integrate over many orbits, many cycles, and weight by the known or measured noise properties of the interferometer that's being used to record the strain of a gravitational signal. So there's the quantity that comes out, often called rho, is the signal to noise ratio. So when you hit the overlap with a buried signal, the signal to noise ratio will spike. And so because you're cross-correlating over many orbits, signals that may not be visible to the eye in the data or even in a time frequency plot can be revealed statistically by this integrated signal integration against a known signal prediction. So to do this, there are a variety of search pipelines. So some of the original ones from the LIGO and Virgo scientific collaborations use different detection statistics to consider when one of these template matches exceeds the threshold and estimate its astrophysical significance. So this could be there's more to gravitational wave detection than just measuring a signal to noise ratio to improve the discrimination against background. For example, in cases where the noise is not perfectly approximated as Gaussian noise, or two of the particular techniques used would be to check that the signal to noise distribution as it accumulates across frequency bins is consistent with a kind of a chi-squared test that's used to reweight the rho into the detection statistic that's compared by a background generated by sliding the results from the two detectors in time so that any coincidence is non-astrophysical, or by generating noise and signal models for a single detector and comparing sort of a relative model probability, a log likelihood statistic, which is done in the GST-LAL. And so these were both used for some of the original first observing run searches and results, and have since evolved and been joined by many additional techniques to resolve signals from the gravitational wave background. Another method used to identify signals, which has been effective for loud mergers as well, is searches that look for transient signals with no assumed model waveform, often using an excess power technique, so decomposing in the time frequency space in some way, identifying and clustering unusually loud pixels, and leveraging the coherence of the signal in multiple detectors to discriminate this excess against some transient that could be better described by a local noise event. So I'll pause there, or I'll move on there from the detection and talk about how once a signal has been identified as something that is likely astrophysical, how you can follow up to interpret what kind of source produced that event. And there's a hint of this, of course, in the templated searches, which template rung up, but that's not sort of, that's not what we really do to figure out what the best masses are and other properties are to describe these systems. So this is a catalog of the binary black holes, black hole neutron stars, and neutron stars that have been observed in gravitational waves so far. You'll notice there's sort of a funnel-y shape to these diagrams, at least at low mass. And this is reflecting that the sensitive volume of the detector is strongly proportional to a mass scale to the 5/2 power. So as we increase the mass of the gravitation of the objects that are producing gravitational waves, the gravitational wave signal gets louder, and we are sensitive to a larger volume of space. So we expect, if rates were constant, to see this kind of proportionality of with increasing mass. At least for lower masses, things get a little more complicated once we're in the higher mass region. Okay, so how do we figure out what we saw? Let's go a little bit more into the details. So what we're going to be doing is matching, again, the kind of waveform model, which depends on mass and which depends on distance, with the pattern that's recorded by the detector using our knowledge of how the detector responds to a given signal. So the results you'll see from this have these sort of chirp, or sort of say for mass and mass, have these banana patterns. So where do these correlations come from, and how do we get from a recorded stream in the detector to plots like these ones that identify correlations between characteristics of the source? So the general idea here is the primary method used currently in the field of gravitational wave astronomy is a Bayesian technique involving calculating the likelihood of the data with a given model prediction. And so just sort of a heuristic explanation is that we have some signal in the space of waveforms. There's some noise around it, which means that when we measure the signal, it's sort of been buffeted around through signal space over here, but we record it away from the noise alone region with some signal to noise ratio set by the scale of noise in the detector. We then do our best to connect this signal to our family of waveform models. We fit the best fitting parameter to the signal that's been recorded, and we use our understanding of the noise properties to estimate the errors in the recovered signal. So here's an example with a Markov chain Monte Carlo run on an injected binary black hole. And the first thing you notice is that if you try and put a waveform model in for the two component masses, what you recover has a strong correlation in the, what you recover has a strong correlation between the two masses. So what you have here is a very precise combination of M1 and M2 called the chirp mass that is precisely recovered by this waveform comparison. And that's because the frequency evolution of the strain as a function of time is a leading order driven by this particular combination of masses. So to understand why the gravitational wave results look the way we do, we need to dig a little bit more into the modeling, what parameters it depends on and how they influence the evolution of the strain. That's coming again from the orbit of the source binary. So the first thing we're going to do, we're going to take our model for the strain as a function of time, that sort of chirp pattern. We're going to convert it to the Fourier domain, and we're going to project it onto the sensitivity of the detector we're considering. The result has an overall scale that's proportional to the chirp mass, inversely proportional to the distance to the source, has an amplitude scaling that comes from the sky location and the orientation of the binary, has an amplitude fall off in the frequency domain. So although the amplitude in the time domain is increasing, there are more signals per frequency, or sorry, more cycles per frequency at earlier times. So the amplitude is largest in the frequency domain at lower frequency. And then a phase evolution, which is really where all the orbital dynamics, the M, the spin, the tidal parameters are going to influence this pattern. So just from the detector response, though, and the arrival time of the signals, you can start to see how a network of gravitational wave detectors localizes the signal. So this is a combination of amplitude consistency and arrival time triangulation between the signals recorded in multiple detectors. So for example, this is 1708-17. Hanford and Livingston had a arrival time timing, and then when compared with the relative amplitude observed in Virgo, this narrowed down the location on the sky to be overhead for a region of the sky where the Virgo detector's antenna pattern was less sensitive. So these sorts of factors coming from this dependence of the amplitude on sky location and the binary orientation give us the sky position. And then we also, from the amplitude of the signal and chirp mass coming from that leading order phase frequency evolution, give us an estimate for the distance to the gravitational wave signal observed. So the gravitational wave phase, again, tracks the orbital phase. The phase coming into the signal that we use to analyze comes from the frequency, the time of arrival, the phase, the chirp mass of the system. And it also has higher order terms that are affected by combinations like the mass ratio, in particular, a combination of spin components taken as a product with the angular momentum of the system as a whole. So this chi effective describes the leading order contribution of spin on the orbital dynamics. And this effective tide combination, which is a little bit messy combination of masses and individual tidal components, which ends up being sort of what's packaged up together against one of these frequency terms, and lets us extract this combo as our best measured combination of parameters, similar to the way the chirp mass is the best measured combination of mass parameters. So Katerina Tiziano has a very nice review going over this process for 170817, which in particular shows things like the effective spin parameter and the mass ratio here. So I'll just put these definitions up as a reminder, have this correlation. So a reduction in the mass ratio could be reinterpreted as, or could be possible with a corresponding increase in the effective spin. So we have to be careful with these high dimensional parameter spaces to understand the influences of our assumptions on one parameter on the recovered properties of another. So, so this is, I'll just sort of, okay, so this is how we get to the kinds of recovered properties of the catalog of gravitational wave observations, like these likely regions for the mass and the mass ratio. This is from the second gravitational wave catalog put out by the LIGO-Virgo-Cagra collaboration. We have interesting spins, effective aligned spin for some of the binary black holes that we've seen. And we also get from the catalog as a whole, things that are that may be interesting to observers, like the merger rates of systems inferred from their observation in gravitational waves. So for example, you can compare for neutron stars, the rate of neutron stars observed inferred from the gravitational wave observation. So of course you need to fold in the sensitivity of your detector, the selection effect that makes it more sensitive to heavier masses, but that's all fairly robustly establishable. And so you get a rate for gravitational waves for mergers observed in gravitational waves that you can compare to how many mergers you might expect based on observing short gamma ray bursts, which seem to be generated by gravitational or the same class of double neutron star mergers, from the observations of galactic double neutron stars and the predictions for how often these types of systems would merge. And kilonova, and then of course the rich exploration of the scenarios of stellar evolution and binary interactions that would generate from the number of main sequence stars the number of compact binaries you would eventually expect to see. I see there's a question about polarization information. Yes, so that is going to come actually more from a multiple detector analysis, which I haven't really talked about, but it is a single detector that's just in this L configuration records one component of polarization. If you have multiple detectors, you can start to compare the data recorded in both of them and get information about the system, the gravitational wave polarization as a whole. Okay. The other thing that is notable that you would get out of the gravitational wave set of observations is understanding of how the masses are distributed. So for example, the black hole masses that we infer from the rates of mergers are falling off as some sort of power law here, but as of the recent LVK publication, we see some potential structure here where the power law turns off at some high mass and perhaps has a bump in the middle. And then we have the most mergers coming from, yes, coming from the low mass systems. One thing I haven't mentioned so far with the analysis based on in-spiral signals is that we also have a possibility of recording that post-merger oscillation pattern. For advanced LIGO, we would expect to be able to capture this only for very nearby sources, but next generation facilities aim to record something like 100 post-merger signals per year. as the duration and the frequency of this oscillation is sensitive to the dynamics of the hypermassive remnant after the stars collide, where temperatures can be more higher, and the lifetime of this system oscillating before it collapses or radiates enough energy to no longer oscillate anymore is very sensitive to things like the transport properties of the matter, magnetic field excitations, and hot equation of state. So I'll close just by saying, I've scratched the surface, focusing primarily on LIGO signals, but we have other areas of the gravitational wave sky, other frequencies that folks are looking at. And I also focus primarily on in-spirals, but there are also things like core collapse supernova, which would give this comparable signal, comparable bursty signal, which could be characterized in terms of frequency and time, or long-lived asymmetries of a spinning neutron star, which would also generate a changing quadrupole moment that you could hope to observe in gravitational waves. So if you're interested, you can try some of this at home. There's open science workshops that have lots of tutorials, Jupyter notebooks you can learn. We'll introduce you to additional friendly LVK people if you have questions about how all this works. But other than that, I'll stop now so I can answer any questions and turn it over to discussion. So thank you.
Thank you, Jocelyn. That was just excellent, really just the sort of pedagogic introduction that I was hoping for, and I learned a lot. And let's open it up for questions from the audience. Please just unmute and go ahead and ask.
Hi, Jocelyn. Do you have any intuition about how well, so if there's people doing simulations that are not like fully general relativist simulations and you do the whole mass quadrupole thing, how would you expect that to be accurate to just like an order of magnitude, or what are the extents of applicability of a simple quadrupole approach?
Well, it depends on how relativistic what you're trying to model is, I guess. So certainly there have been qualitative successes in exploring the frequencies of post-merger oscillations with conformally flat approximations to the dynamics and this kind of quadrupole approximation. So yes, there's a place for that. Exploring sort of the relative import of novel features. I think that's essential. Now, I don't know if even a fully GR simulation is at the point where we can have, phase accurate, reliable predictions of the merger regime. So, so in that same context, we may be driving our interpretation by these kind of qualitative questions anyway. But that's a rapidly evolving field, so stay tuned.
I see that there's a question in the chat from Pravir. The question states, yes. What are the drawbacks for machine learning-based parameter estimation as opposed to Bayesian?
Well, those two aren't necessarily mutually exclusive. Typically, a machine learning approach can be used within a Bayesian framework, either to describe your model in an effective way, or to, there's some, interesting techniques of likelihood-free parameter estimation, which, so folks are starting to look at these. So you would have to be a little more specific as to what machine learning you're interested or you're considering before I could compare it to a specific parameter estimation.
So I was more concerned about the way where we put in the distribution for our background equation of state parameterization and use a deep learning model to get out the deep learning model or use a Bayesian neural network model to get the distribution of posterior distribution of our equation of state model. So we start off with our prior equation of state distribution and use Bayesian neural network or Bayesian deep learning to get the equation of state.
So you're starting with an equation of state framework for some parameters using machine learning to generate the waveform model and compare it to the data and get the noise spectrum and get out the likelihood?
Yes.
Well, I don't know how well that works. I imagine it would be challenging to test.
Okay. But there are a couple of papers that essentially do similar things, but I'm not sure. So for some reason, they are not comparing it against the traditional ways of parameter estimation, and I was wondering why is that so? I mean, it's more like they try to present their results as a mutually exclusive thing, and I'm not able to understand why they don't compare with the traditional approaches. For example, there's this recent paper. I can follow up.
Maybe we can follow up in the Slack, because
Yeah.
I'd want to see exactly what the details are to be able to answer that.
Sure.
But yeah, I'd be happy to.
Thank you.
Are there other questions from the audience?
Plenty of technical details I could know.
I don't see any. So I have a couple of questions, Jocelyn. Some of them are very naive. The first question is, when you talk about parameter estimation, you also have to make a choice about the time domain over which you're going to look at the signal, or the frequency domain over which you're going to look at the signal. How does that affect the outcomes? I've heard discussions about, for example, the tidal deformability being sensitive to whether or not you keep some of the early cycles or some of the late cycles. So where does all of that come into the data analysis?
Yes. So so there's let's see. So there's the frequency range, which is useful to you, is limited by the calibration of the detector, which is validated in a restricted frequency regime. The Nyquist frequency of the data set you're working with. But beyond that, the waveform model that we use for tidal in-spiral, for the tidal effect on in-spirals, we have competing effects of at high frequency, increasing tidal signature, but also increasing model uncertainty. So there have been some explorations of modifying the high frequency cut and seeing the influence on what you recover. Broadly, the result is that I don't actually have any posterior distributions for tides here, but your distributions become broader if you cut off the highest frequencies, but they also become more consistent between different modeling approaches. For the low frequency, yes. So because all of these parameters are correlated, your precision, the precision with which you pin down the chirp mass, the mass parameters, and the spin influences the strength of the conclusions you can draw about the tidal parameter, even though the signature of tides only becomes strong in the final orbits. So you do need to make sure you have a self-consistent waveform model that tracks from the early in spiral through to the merger to get the best, again, the best interpretation of the tidal effects. Not sure if that quite asks what.
Yeah, no, it addressed the question I had in mind. But for GW 170817, for example, the 13 kilometer upper, roughly 13 kilometers is being talked about as the upper bound on it. And so how would that change if you were to just look at the last few cycles?
Well, so the challenge there is you don't, and it's not like you can look at the last few cycles in the time series and see them, right? So if you try to just narrow your, like you really require the early in spiral to anchor where you expect the coherent phase evolution of the signal to go. And so you can kind of do this cross correlation type thing through yeah. So
Yeah,
I mean, so this is, yeah, like so the idea would be like, if I modify the final orbits of a cycle that's, buried in noise like this, unless I know very well from the early frequency how coherently how that signal is expected to change at the high frequency, I can't make an independent tidal measurement.
okay. Still don't see any questions from the audience. I'll keep going. Is there a bound on the tidal love number that you can deduce from, say, maximum mass of neutron stars and the first measurement of the tidal deformability from GW 170817?
I didn't put any observational results in this, so you're asking me tough questions to point at things. So the question is, so with the maximum mass and 170817.
Right. I mean, yeah. This is more like a discussion rather than this specific question to you alone.
I mean, I could stop sharing my slides maybe so we can see each other.
Okay. Yeah. Okay. So I forgot I was recording. So maybe we can also stop recording. The select was done. Hold on.